frequency distribution. So here's a table that describes all the various different ways to describe a set of numbers. We call all these different ways of describing a set of numbers descriptive statistics. So this table summarizes for us here in the very first column types of variables: nominal, ordinal, interval ratio listed twice, one in the case that the data is skewed and one in the case the data is normal. Now, we haven't talked about skewed or normal distribution, but we did talk about different types of variables in the previous lesson. Regardless of any type of variables, we initially put all the data together and create a frequency distribution, and that's what we do with individual scores. So that's the topic for today. And then we will talk about measures of central tendency, which are different ways of measuring the average. And then we're going to ask, how are the data distributed? How much do they vary? And there are different ways of measuring the variability of a set of numbers. And lastly, under descriptive statistics, we'll talk about how variables are related to each other by calculating and looking at correlations. But first, let's look at individual scores and how we put the data together on a table to kind of find a way to organize the data. Now, here's some data that I've created and put together in a very organized table. Ice cream flavor. Here we see 3 different ice cream flavors: chocolate, vanilla, and strawberry. And here in the second column, we have frequency, which is to count how many people selected chocolate as their favorite ice cream flavor, or vanilla, or strawberry. And you see here that there's 100 people that answered this question. And as you can see, of the 3 ice cream flavors, chocolate is the most popular ice cream flavor because we see that the frequency is the highest. Well, that has my little personal bias because chocolate is my favorite. And this data was created with that personal bias. But nevertheless, just to illustrate, and then you see in a full frequency table at the percent column that lists the percents. So if we had 100 people, just to make numbers easier to follow, that would be 100% of the people. And 41 people who like chocolate would be 41 out of 100, which turns into 41%. Similarly, 20 out of 100 is 22%, 37 out of 100 is 37% for the total of 100. Sometimes rather than saying 41 people like the chocolate flavor, if you said 41% of the people like the chocolate, that makes better sense. That gives you an idea, the context within which you've calculated the percent. And then in SPSS, you will see a valid percent that's listed here. In this case, they're identical numbers in these 2 columns, the percent and the valid percent. But sometimes there will be, on surveys, for example, a person or two that skips this question. Maybe the person decided to skip this question because they didn't know how to answer the question, because their favorite is not listed on here. Their favorite is maybe Rocky Road and it's not listed. So then valid percent would be calculated based on the valid number of responses. So if one person skipped this question, then valid percent would be calculated based on 99 people as being 100%. So you'll see a little bit of a discrepancy between valid percent and percent in that case. And then you have the cumulative percent here, and you'll see the pattern of the percents being added up from one line to the next. You see 41% here, and that's chocolate, 41%. And then 22% for the vanilla flavor accumulated would be chocolate plus vanilla, which would make it 63%, and then adding 37% more to it, which makes it 100. So we see the percents accumulating as you go from one line or interval to the next. In the frequency tables that we will do, we'll see the cumulative percent added from the bottom to the top, so that we're able to make it align to the formula we will use to calculate for a percentile. So here's a set of numbers here. What would you say would be a good description of what's inside the box? You see numbers, and you'll see numbers in teens, right? And one might say the numbers vary from 10 to 17 as the highest. And one might say, oh, there's some numbers that repeat. And if I were to ask you what you think would be the midpoint or an average, without calculating, just estimating, you might say, well, maybe 13, 14, around there, okay? And so believe it or not, if you were able to follow along that description and you agreed with those descriptions, then you're pretty much done with the descriptive statistics. But we want to find a better organized way to really present what's in this box here. There are only 18 numbers here, but imagine 18,000 numbers. Okay? We wouldn't want to stare at 18,000 numbers and try to come up with some kind of pattern and come up with some descriptions like the ones that we just talked about. So thus, we do a frequency distribution. In a frequency distribution, you would want to list all the scores, all the possible scores that's inside the box, from the highest to the lowest. And so here's the scores column, and we're listing the numbers with the highest, 17. Just go down in sequence until you reach the smallest number, which is 10. Right? So here's a sequence of numbers in the first column. And then in the second column here, called the F column, and you may have guessed that F stands for frequencies. How many times does each score occur? So these numbers represent the repetition, the number of repetitions of this data. For example, 17. How many times do you see the number 17? Well, there's only one. So the frequency is going to be 1. 16 doesn't exist in this table, but it was listed here just for the sequencing of the numbers listing all the way down to 10. So the frequency there is going to be 0. Then you have 15. You got 15 4 times. So here's the frequency of 4. And then you have, in a similar way, 14. You will find them 6 times. So here's 6. 13 occurs 4 times. 12 once. 11 once. 10 once. So if you were to add up all the frequencies, just to make sure that you didn't overcount or undercount, they should add up to 18. And that was the number that we mentioned earlier about how many scores you would see in this box. And the notation we use to indicate the number of scores is the capital letter N to represent the sample size. So in this case, the sample size is 18. There are 18 scores, and it checks that if you add up all the frequencies, they add up to 18 as well. There's a saying, a picture is worth 1,000 words, right? So here is a graph. Let's look at the same data and look at this graph here. You'll notice that these are bars creating a certain shape. You also see the bars are detached from each other. Okay? There's no attachment of this data. This kind of graph is called a bar chart because they're just bars. And you'll see 2 other types of graphs that I will talk about. But this is called a bar chart. The tables are, or the graphs, bars are detached from each other. And it follows the shape of the frequencies in the frequency table. But before we begin to look at the graph a little bit more carefully, you'll see the vertical line that's labeled as count and the horizontal line that's labeled as scores. So we want to list the scores in the way that they appear in the frequency table. And because where the 2 lines meet, the vertical and the horizontal, we want to place a 0 there. That's the lowest point. So the numbers increase on the horizontal line from left to right, and the numbers increase in the vertical line from the bottom to the top, where the two lines meet being the smallest, right? So we typically put a 0 there to remind us that that's the beginning point for both the vertical and the horizontal line. So then we would have to list the numbers from the least to the greatest. So we're almost having to read this table from the bottom to the top, right? So beginning with 10, and then 11, 12, 13, 14, 15. And notice that 16 is not there. You could put it there and it would have no bar above it because the frequency was 0, or just skip it for aesthetics reasons. And then in the vertical line is a scale 1 through 6 in this case because the frequencies go up to 6. That's the highest point. So I just created a graph here, or a line of a scale from 1 through 6. So then let's look at the table and see if we can see how the graph was created based on this table. So the score 10 has a frequency of 1. And so here it is. This bar represents the score 10. And then score 11, 1. The score 12, the frequency is 1 again. So they're all the same height. And then 13 goes up to 4, 15 up to 6, then back down to 4. And again, 16 is missing, right? Could be there, doesn't have to be there. And then 17 is a frequency of 7. So when you look at this graph, you kind of see the distribution and where you see the most number of scores are, which in this case is between about 13 to 15. And you would expect the average or the midpoint to be around those numbers as well. But there's an innate problem with this slide, and that is that these are bar graphs, which means the bars are detached from each other. So how do you account for the numbers in between or the spaces in between when you have the data that is continuous or numerical? Right? Scores is numerical. And notice here that at the top of the slide it says the bar graph is used for categorical data, right? And so scores that you see here is not a categorical data. So that's the problem with the slide, right? This is indeed a bar graph, but it would be useful for categorical data. And you remember from the previous lesson that categorical data are data that has categories like ethnicity or gender, and this by far is not categorical but numerical or continuous. So let's look at a better graph for continuous data like this in the next slide. Here you see another table of frequencies, and this time we're asking the question about stress rating. So on a scale of 0 to 10, what is your stress level? With 10 being the highest level of stress and 0 being the lowest level of stress. And you can see the frequencies here. These are some big numbers. So what would happen if you added up all the frequencies? What would you get? The total that you would get would be your sample size, or n. And that number, when you add up all together, is going to be 151. And you can check to see that that's true. So we have a sample size of 151 people, and they were asked a question to rate their stress level on the scale 0 to 10. When you look at the frequencies, you kind of see where most people are congregated, right? Maybe around here. Right? You see a lot of numbers here, and you kind of estimate that that would be sort of the mid-range as well. So it looks like most people said 7 or 8, and that's probably pretty true for most people. Right? Maybe all of us thinking about our own stress level. Well, it's kind of a dangerous question to ask when you're talking about statistics, right? But that aside, people tend to be stressed. And so I don't think that this is too far away from an actual survey data. But when you see how this continuous data is transposed onto a graph, and you notice on this graph, the bars are attached to each other this time, accounting for all the numbers in between this continuous data. When you see the bars attached to each other in this way, it's known as the histogram. And histogram is used for continuous data. And when you see how the stress rating going from 0 to 10, from left to right, is listed here, and how the frequencies look in a picture, you kind of see the stress rating 7 and 8 kind of here, right? That's where most people are. Kind of see a pattern like this. So this is known as the histogram. Now, if you had a lot of different levels, graphs or bars, sometimes it's better to just connect the dots that creates that shape that I just drew. Same data, and you kind of see the line there, just following the pattern and connecting the dots, so to speak. This is used for continuous data. So when you have continuous data, you can use the histogram or polygon. You have a choice there. With the polygon, you want to make sure that the number or the line that represents the frequencies is not kind of floating in midair. So we anchor it down to the horizontal line with 2 dashes in between, or just bring down a dotted line to kind of anchor it to the horizontal line. Let's look at another table here before we add more to it. You see scores ranging from 1 to 6. And then you see frequencies. So what would you notice? Let's say these are test scores. Did the students do well on this test? And how many students does this table represent? You might say, only one person got a score of 6. No one got a score of 5. 2 people got a score of 4. 3 people got a score of 3. And then 10 students got a score of 2. And 4 students got a score of 1. If you were to add up all the frequencies, you would get your N of 20. So because 10 students got a score of 2, that's 10 out of 20, or half of the students got a score of 2. Maybe it was a very tough test to begin with. In a full frequency distribution table, you would find what's called a relative frequency. Relative frequency provides to the person looking at the data how frequencies look relative to the total N. Right? So if I were to go up to someone and say 10 students got a score of 2, a typical response would be 10 out of how many? Right? 10 out of 20. And that's what relative frequency is. In terms of calculation then, relative frequency would be frequency relative to N, or frequency divided by N. So if you were to take the frequency for each and divide it by 20, you would get your frequencies. And when you do these divisions, you'll notice that the relative frequencies are very tiny. And it is to divide up, if you were to imagine a big pizza, it's to divide up the size of the frequency in terms of the big pie that totals 20. So you'll notice that these numbers then, if you were to add up, would add up to 1.00, one big pie, distributed in this way. And you notice that 0.5, that's a whopping half, right? So that's 0.5 of the total of 1. Now, if you look at the relative frequencies, it's kind of hard to imagine how you might use these numbers. These numbers are not used by themselves very often, but you will see how these numbers are similar to this column that I'm going to bring up, which is the percent column. So take a look at the similarity between relative frequency and the percent columns. You see that relative frequencies, when multiplied by 100, right, in the similar way, you're basically turning those numbers into percent. So 0.05 becomes 5%, and 0.0, of course, remains at 0%. 0.10 becomes 10%. So whenever you multiply a number by 100, the decimal place actually moves twice to the right, right? All right, so you see 15%, 0.5 is now 50%, and 0.2, 20%. Percents are easier to understand because it does provide the relative information, right? The context that these percents are based on 20 people. So I can say 50% of my students got a score of 2. Well, that makes sense, right? That's half of the people. And then you have the cumulative percent, which compared to the percent column, from the bottom to the top, accumulates the percents. Similar to the table that you saw earlier about ice cream flavors, the same idea. But you see the percents accumulating from the bottom to the top. So you start out with 20 because this percent column begins with 20, and that's for the score of 1. To find the total percent, of scores 1 and 2, that would be 4 and 10 people together, which means to add 50% more to it, which makes it 70%. So 70% of students got a score of 2 or 1. And then if we want to know the total percent of those who scored 3 and below, we would be adding 15 more percent to it, which makes it 85. And then 10% more, which makes it 95. And it remains at 95, and then 5 more percent, which makes it 100%. So at the very top of cumulative percent, you should always add up to 100%, which accounts for 100% of your data. Now there's a column that we skipped, and that's the CF column. C stands for cumulative, just like the cumulative percent, and F, which we know is frequency. So this column, CF, is cumulative frequency. And in the same way that we accumulate the percents from the bottom to the top, cumulative percent takes the frequency column and adds from the bottom to the top. For the score 1, frequency is 4, so we're going to start with 4. And then we're adding 10 more students, which makes it 14. Adding 3 more students to that, which makes it 17. 2 more, which makes it 19. And then 1 more, which makes it 20. Now, that's a number that we've seen before, right? 20. And that was a number of the total sample, right? So the CF column has all the frequencies added up from the bottom to the top. So by the time you get to the top, that top number should be identical to your N sample size of 20. So it's not a coincidence that 20 at the very top is the same as your N, because this is how it should be. Now we want to talk about percentile rank and how we might calculate, because we noticed earlier in this data that the student scores are pretty low. So if I got a score of 3, should I be happy with my score? 3 is a very low score, but when you have a score of 3, 2 other people have the same score, but look how many people scored less than you, right? 10 plus 14. 14 people in the class of 20 scored below you. So I would be pretty happy with the score 3. But because the scores are generally low, your percentile rank is going to be pretty nice, maybe above 50th, right? Because there's 14 people who scored below you. So percentile rank is a calculation to help one understand where you stand relative to other scores. Typically, a percentile rank that I've seen very often when taking my kids to the doctor when they were young is the doctor would measure their height and tell me what their percentile rank is. And my son would always typically be somewhere between 90th percentile to 95th percentile rank. And that always made me happy, because at least that tells me that I'm feeding him okay. And so between 90 to 95 percentile in his height would mean that if you were to line up all the kids at his age, he would be at the very end of that line. He would be pretty tall, within the 10%, top 10% or 5% of height. So percentile rank differs based on other people's scores. And before we calculate for the percentile rank that has a big formula that comes with it, I'd like to mention real limits. Now, real limits are not really real, right? That sounds funny, right? But real limits have to do with how much a typical score, say 5, would range, right? Halfway up and halfway down. The real limits are hypothetical numbers as to how far a score can go down, what the range, a full range of a particular score would be. So the real limits for the score 5 would be halfway down to 4.5 to halfway up to 5.5, right? So these become the real limits for the score 5. Let's do another one. The score 4, halfway down would be 3.5, right? To halfway up, which would be 4.5. Now, one might ask the question, well, there's kind of an overlap there. How can there be an overlap? And these are just hypothetical ranges, and so these are not actual scores. We just want to have an idea of what a typical score can range. So you'll find that when we calculate for a percentile rank, you will need this information for a particular score that you want to see the percentile rank of. When you see a range of scores like this on the real limits, the lower numbers, right, so the numbers on the left are known as the lower real limits. And then the top ones, or the upper ones, are known as the upper real limits. And you'll see that the percentile rank formula will ask for the lower real limit. So if we wanted to focus on the number 3 to see if I should feel great about that score, the formula will ask for a lower real limit, which would be halfway down, right, 2.5. To find the percentile rank of a score, here's a formula. Now it looks like a very, very big formula, and it is to calculate for a percentile. And you'll see big parentheses here, and within which you have a lot of things going on in the top, or the numerator. You'll also notice that in the numerator you have another kind of fraction sitting right up on the top. So let's read through this. CF below interval. Well, we know that CF stands for cumulative frequency, right? So cumulative frequency below interval. Now, interval refers to a line on the table, and you'll see this word pop up 3 different times in the formula. So that interval is going to be an important piece of information. And then in parentheses, you see the score. That would be the score that you want to see the percentile rank of, minus LRL. Now we know that this LRL from the previous slide means the lower real limit. So the lower real limit of that interval divided by the interval size, close the parentheses, and then F, and F stands for frequency within interval, all divided by N and multiplied by 100. So here's a table that listed the same scores that we saw previously and the frequencies. And I've taken out all the other columns because for this formula, we really need to have the CF column only, and then the real limits. So let's say we want to calculate for a percentile rank of the score 3, right? I want to know if I should be happy with that score. So we go right to the score 3 in the scores, and you notice that this whole interval or line has been boxed in, because that interval is what I want to focus on, and that interval is what these intervals here, these 3 times the interval, the word interval appears, focuses on. So let's see if we can plug in these numbers based on, according to this formula here. Again, we're trying to calculate for the percentile rank of the score 3. You see that around this boxed interval that we're focused on, the CF below interval quite literally is the CF below interval. And that would be 14. And the score is the score 3 that we're trying to convert. And then frequency within interval, quite literally, is frequency within interval. Then you have the lower real limit, and that's the lower real limit of the interval that you boxed in, and that's 2.5. And it looks like the only thing that's left is the interval size. Well, interval size, as you see here in the bottom, is calculated for the difference between the upper real limit and the lower real limit, or taking the upper real limit of 3.5 minus 2.5, which is 1. Another way of calculating or figuring out what the interval size is to ask the question, in each interval, how many scores do you see? And in other frequency tables, you will see ranges of scores represented in each interval. But in this particular table, you see one number here, one number here, one number here, one number, one number, one number, right? One number represented instead of a range of scores. So we can count with our hand, the interval size is 1. And then, of course, n is 20. So you see that all the numbers are plugged in based on the table that we see here. So let's see if we can calculate. With the same formula that we've seen before, here's how the numbers have been plugged in. 14 plus 3 minus 2.5 over 1 times 3, all divided by 20 times 100. So at this point, it's mathematical, right? So let's take care of the fraction within fraction first, and I'm going to carry everything else over. So 3 minus 2.5 is 0.5 divided by 1, carrying everything else over. Now I want to still take care of this first because multiplication or division takes priority over the plus or minus, right? So 0.5 over 1 is 0.5 times 3. 0.5 times 3 becomes 1.5, carrying everything else over. And then 14 plus 1.5 is 15.5 over 20 times 100. And then 15.5 divided by 20 times 100 becomes 78th percentile rank, because the number is 77.5. So the original question was, what is the percentile rank of the score 3? And although it's a low score, the percentile rank we suspected would be higher because 14 people in the class got a score less than 3. So with the score of 3, the percentile rank is 78. All that calculation just to be able to plug in this information here. The score 3 is 78th percentile. Now, should you be happy with the score 3 at 78th percentile? I think that's a pretty good percentile. You're above average. And with the same formula and a similar calculation, you can try calculating for the percentile rank of the other scores and see if you can fill them in just for practice.